Stanford University.
First, we start with symmetries, and I'll remind you of a few things about symmetries, because supersymmetry, if nothing else, is a symmetry. Symmetries always relate things. And what they do is they relate things which are related by being transformed in some way. A particular symmetry is left-right symmetry. My left hand and my right hand are symmetric, and if the world and I and everything about me has left-right symmetry, then my right hand weighs exactly the same thing as my left hand, would be exactly as strong as my left hand, and would be in every respect identical to my left hand. And in that sense, symmetries relate objects which may be different but symmetric. In particular, those objects that are related by a symmetry generally have the same mass. So let's talk a little bit about the mathematics of symmetries. We've already talked about some symmetries, in particular things like rotation symmetry in space, and now I'm thinking about continuous symmetries. Whether supersymmetry is a continuous symmetry or not is a question which has no answer. It has no answer because it doesn't fall into the category really of things where the question actually makes sense. But let's just review a little bit about symmetries. Symmetries are operations on a system which are described quantum mechanically by, first of all, operations, but operations are described by operators. Operators on state vectors. We start with a state vector, whatever it happens to be. I don't care what kind of system it is, it's described by a state vector, and we apply some symmetry operation. The most well-known symmetry operation that I can think of is rotation. Actually, I can think of an even simpler one, just translation of space. Then the operation would simply move an object from one place to another. Right? But let's take the case of rotation as a more representative example for the moment. What's the mathematical symbol to represent a transformation? A unitary operator, a unitary matrix or unitary operator. This unitary operator here could represent rotation in space. You would have to indicate what the axis was, and you would have to indicate what the angle was. But once you did so, there would be a unitary operator. That unitary operator acts on any state to give a new one, which is a rotated version of the same thing. Yeah.
But it operates on states, not on space. It's not rotating states.
It's the operation of rotating an object. It rotates, it acts on objects. That's right. It acts on states, but states mean collections of objects. And this is the operation which rotates everything. Just rotates everything in space. So it takes whatever the state is. Well, I'll give an example. The state might consist of the mathematical representation of a particle over here and a particle over here. All right? So this is a state which represents two particles, one over here and one over here. A rotation about an axis, a rotation incidentally always takes place about an axis, let's say about this axis, it will simply give you a new state in which this particle has been rotated to here and this one to here, and so it's a new state with a particle over here and a particle over here.
But isn't the state vector an element of a Hilbert space?
Yes.
So that's an infinite dimensional vector.
It is.
And are we rotating the Hilbert space, or are we rotating three-dimensional?
Both. It's the rotation in Hilbert space that represents the rotation in space.
It's like a next step up.
Yeah, right. That's right. It's right. Both. All right, but this is the rotation that we do on the Hilbert space. Now, it's not strictly a rotation. It's a unitary transformation, which is similar to a rotation. So it's both a transformation of the Hilbert space, and it represents the act of rotation in space. Okay? All right, now, as I said, U represents a rotation about an axis, about a certain angle. There's particular transformations which are especially interesting to us. They're the infinitesimal. Oh, well, before that, let's talk about, very briefly, about the properties that a symmetry operation has to satisfy. The most important is that it has to be unitary. Unitary means that its Hermitian conjugate is its own inverse. This is the unique property which says that state vectors maintain their length. It's actually just probability, conservation of probability, that this vector should have the same length in the Hilbert space, the same norm in the Hilbert space as the original for every vector. That's the condition that U be unitary. That's why it's called unitary, because it's called unitary. All right, now there's a special family of these which are very small rotations, rotations by very small angles. Now, every place I say rotation, you could substitute other interesting group operations, but let's stick for the moment with just ordinary rotations. The infinitely small rotations, infinitely small means by an infinitely small angle. A rotation by no angle at all, in other words, no rotation, that's not represented by U equals 0. U equals 0 is not unitary. It's represented by U equals 1. So an infinitely small rotation is just U equals 1. Well, supposing you want to rotate a little bit, not quite 1, then you have to add something, and if the angle is very small, let's say the angle is epsilon, epsilon is a small number, then you have to add epsilon times something, and in order to make it unitary, you have to add I times a Hermitian operator. Call it L. L remembers the angle of rotation is epsilon, but L has to be indexed by a direction of space. So this could be rotation about the x-axis, for example. It could be rotation about the y-axis, or it could be rotation about the z-axis. Or it could be rotation about some other axis.
Or a sum, perhaps, x, y, and z, or...
Well, if you sum them, you wind up getting a rotation about some axis, which, intermediate axis, that's right. So there's 3 basic ones out of which you can build all the small rotations. An arbitrary axis is just a linear combination of rotation about x, y, and z. All right, that's the, and it's easy to check that if L is Hermitian, then U is unitary, at least to the leading order in epsilon. We're going to study things to orders, to lowest orders in epsilon. Now, one of the most important things about a group of symmetries is the commutator algebra. There's a mathematical concept, the commutator algebra of the generators. These are called the generators. These are called the infinitesimal generators, the L's, and they satisfy a commutator algebra. I'll tell you first what a commutator algebra is, and then I'll show you how it's connected to these transformations. First of all, mathematically, what is a commutator algebra? It's basically you take the independent generators, in this case, rotation about the x, y, and z axis. You call them Lx, Ly, and Lz, or better yet, just L sub I. And a commutator algebra is just a closed set of relations that if you commute any one of the L's with any other one of the L's, you get back something proportional to an L again. There are some constants that appear here. All right. So for example, let me write down exactly what you would have for Lx, Ly. You would have Lz here, but that's not quite right. What am I missing? I. And then cycle it through. Ly, Lz equals I, Lx, and so forth, but you can summarize them all by writing I epsilon ijk lk li lj. This just says epsilon ijk is just a symbol which is 0 if any of the two of them are the same, ij and k, and it's either +1 or -1 depending on whether this is an even or odd permutation of 1, 2, and 3. All right, and all it says is Lx with Ly, commutator Lx with Ly is ILZ, and so forth. All right. Now, what's the meaning? What's the meaning, the geometric meaning of these commutator algebras? What are they saying, and why is it important that the generators close under commutation? The right word is they close under commutation, which means the commutator of any two of them is another one. This is called a commutator algebra. Why is this important? Well, what it really has to do with is the following operation. You take a rotation represented by a u. Now you take another rotation about some other axis by some other angle. Let's start it out, u, and then you multiply it by v. What is that? That corresponds to a rotation about an axis followed by another rotation about another axis. Then you undo the first one. So far what we've done is rotate, rotate, then rotate back along the original axis by minus the angle that we originally rotated, and then undo v. Does that give back no rotation at all? Does it give back no rotation? No. The answer is no. If you rotate about an axis and then rotate about another axis and then undo the first one and undo the second one, it is not the original configuration. It is not equal to the identity. It is itself a small, another rotation. Just, most of you have seen a demonstration of this sort of thing. What happens if you rotate a thing about the x-axis, then rotate about the y? I can't do this, but you rotate about the x-axis, rotate about the y-axis. Now I've forgotten which the x-axis is, and do it again and come back. You come back to some other configuration.
Consider an airplane and roll, pitch, and yaw.
What's that?
Consider an airplane and roll, pitch, and yaw. That makes it easy.
I hope never to be on an airplane where I can sense the commutator. Right. Right. All right. Let's check what you get. In other words, what you get on the right-hand side is some other rotation. I won't give it a name. It's another u. It's another u. But let's see what happens if we do it for small rotations. Let's check, in fact, exactly what happens for small rotations. And let's take the case of a rotation about x, a rotation about y, reverse the rotation about x, and then reverse the one about y, but each one of them being small rotations. And let's see what we get.
You know, I think that there's something that you know so well that you haven't mentioned, but when you did the u dagger u equals I, that could also be written as u dagger equals u inverse.
It does.
And so when you see something like you just wrote up there,
Absolutely.
you're doing the inverses of daggers.
Good. So let me rewrite it then the way you would like. We started with u, then we did v, and then we undid u. I wrote u dagger. You would like me to write u inverse.
I just like people to be aware of that.
Right. I know you do. So do I. That's the same operation. Same operation. And incidentally, if we were just rotating about a given axis, let's say one axis, the x-axis, we're never going to go from x to y. What would happen? Rotation by x, rotation by another x, then undo the first one, then undo the second one. What do we come back to? No rotation at all, okay? So if we do everything in one plane, we don't get anything interesting. It's if we do it in two planes that we get something.
The thing you can do with that is you can put one of the v, the second v on the other side, and if u inverse v, u equals v.
You can do lots of things. Let's see what happens. We start with u. That's 1 plus I epsilon Lx. That's rotation about an angle of epsilon. Then we're going to rotate about the y-axis, and I'm going to use a different angle. I'm going to call the angle delta now. 1 plus I delta Ly. Then we're going to undo the first one. That's 1 minus I epsilon Lx. Incidentally, for small rotations, to infinitesimal, the inverse operator is just 1 minus I epsilon instead of 1 plus. And then finally, we undo the last one. 1 minus I delta Ly. And let's see if we can figure out what we're going to get. There's a lot of terms when you multiply these all out. And some of them will get mixed up with others. Some of them will be order 1. In fact, there'll only be one which is order 1. It's 1 times 1 times 1 times 1. The next thing will be order delta. Let's see what's there to order delta, just delta by itself. Well, there's going to be I delta of y times the rest of the 1's, right? So there'll be a minus I delta of y times 1 times 1 times 1. But then there'll be plus I delta y times 1 times 1 times 1. So they'll cancel. All right? Same thing of the I epsilon x. There'll be 1 times minus I epsilon x times 1 times 1. But then there'll be the opposite from this one over here. So the things to order delta and the things to order epsilon will cancel. Okay? Nothing left of them. There are things of order delta squared and things of order epsilon squared. I don't want to keep track of them. You can keep track of them another day. What I want to keep track of is the things of order epsilon times delta, the things which are sensitive to the fact that I rotated about 2 different axes. One of them, the epsilon kept track of the rotation about the x-axis. The delta kept track of the thing about the y-axis. So let's see what's there, what remains there, to order delta times epsilon. Here we're going to have delta times epsilon will always involve Ly times Lx. How many of them are there altogether? How many delta times epsilons are there? There's one over here. There's one over here. And what have I missed? I have missed this times this, right? This one times this one.
Third term times the fourth term.
What's that?
Third term times the fourth term.
Third term times the fourth term. Yeah, third term times the fourth term.
First term times the fourth term. First term times the fourth term. You got that?
Just got it.
We have the first term times the fourth term? First term times the fourth term. It's getting too complicated. I need to clean it up. All right. Oh, there are 2 terms and 2 terms. That's the point. Yeah, right. There's, good, thank you. Here's a delta times an epsilon with a sign which is Ly times Lx, right? Right. Ly times Lx times minus I, I think is minus 1, right? Okay, and then there is Ly times Lx over here, and that comes in with what sign? With the opposite sign. I don't like that. Okay, let's see what happens. So that cancels this? Does? Same sign or opposite sign? Help me, help me. Same sign.
But it's the same order.
No, because I is a minus, right?
Minus I. Minus times minus is plus. And, wait, sorry, minus times minus is plus over here, and then we also have Ly times Lx over here.
The minus times the minus is a plus times the I and a I.
Right, so it's times 2.
So it's a minus.
Yeah.
Yeah, so it's minus 2.
Minus 2, right? Yeah, minus 2. And now we have, that's Ly times x. Now we have Lx times Ly. Lx to the left, Ly to the right. Oh, what do we have for that? I hope it's twice plus 2. Is that look right?
Yeah.
Yeah. Yeah. There are two terms with minus sign, two terms with plus sign. The terms with minus sign are Ly times Lx, and the term with plus sign are Lx times Ly, I hope. So let me just check it. Ly times Lx is minus times minus, and Ly times Lx is plus times plus. Those have the same sign. All right? Then there's Ly, then there's Lx times Ly, and that has the opposite sign. So there are two Ly Lx's and two Lx Lys. If Lx and Ly commuted, then this would cancel. Okay? Then this would cancel. But the fact that these rotations don't cancel, the fact that a rotation, another rotation, followed by back again, don't cancel, are an indication that this should not be 0. In other words, the commutator between Lx and Ly is the thing which keeps track of the fact that rotations in different orders don't cancel out. That's what the commutator really is. The commutator is the non-cancellation of operations which, which don't cancel. That's what this is indicating here. So what does this tell you? This tells you the commutator of, this is the commutator, this is twice the commutator of Lx with Ly, twice the commutator of Lx with Ly, that's what's left here, plus 1. There's also the 1.
You know, I think that we're off by a factor of 2 because there are really 3 terms with Ly Lx and 1 term with Lx Ly.
No.
Yeah, that's what I get to see what you tell me.
So what happens
Yeah, I think that's right. That's what, yeah.
is 2 of them cancel
Yeah.
out of the 3, and you're left with 1 and 1 of the other.
That's what I thought. So what is it? Just 1 times? Yeah, that seems right. There are 3 with 1 sign. No.
3 with 1 order.
3 with 1 order, and 1 with the other order. Remind me. Just.
Yeah, 3 with Ly Lx. It's because all the Lys are on the left of all the Lx's. So if you go to the Ly, you have 2 Lx's to the right. Okay. You go to the L. If you're looking for, what is it?
I've done this at home a number of times just to make sure I was ready for you today.
There's one way to get Lx Ly, and that's the middle one.
Ah, Lx Ly, right. So that's this one.
Yes.
And then there are 3 others.
This Ly has 2 Lx's to the right. That Ly only has 1 Lx to the right.
Okay, sequence, you still get
Do you get this? Okay, good enough. Good enough. I'm blind by now. I can't do it. Anyway, this is what you get. You get something proportional to the commutator here. So in other words, the net answer, there was an epsilon times delta. Epsilon times delta. No 2. All right. All right. Lx times Ly, or the commutator of Lx times Ly, this becomes 1 plus I epsilon delta Lz. In other words, this combination of rotations about x, y, then back again along x, then back again along y, give you a small rotation by an angle epsilon times delta about the z-axis. Right? This is what the commutators tell you. So whenever you have a group of transformations in particular a continuous group of transformations, the whole structure of the group is contained in these infinitesimal generators, and especially in their commutator algebra. The commutator algebra is sort of the group multiplication table, but in the form of these infinitesimal generators. All right, that's
If you switch the U dagger and V dagger, then it will equal the identity, correct? In other words,
Yeah, if you switch the middle.
yeah, you switch the middle. Yeah, if you don't want to switch the middle.
So does this get more complicated if you have 4 instead of 3? You have X, Y, and then there's Z, which is the third. But if you go to 4, now it has to be.
It does get more complicated, but it does get more complicated. But if you know the commutator algebra here, you can, in principle, figure out how to compound together many, many little transformations. This was just one example. You can obviously build up any transformation out of lots of little ones. So if you know how the little ones combine, that's very much knowing the properties of the group, knowing the algebra and the whole structure of the group. All right, so that's what a commutator algebra is. It's a convenient form for representing the whole structure of the group and how the operations intertwine among themselves. Now, next statement, things that I'll remind you of. Incidentally, in the case of rotations, L is of course just the angular momentum. I picked it just, there are other transformations of space besides rotations, incidentally. There's translations in space. Let me fill out the rest of the rest of the group of transformations of space. These are the rotations, and they're rotations, for example, about the origin. The other things you can do with space is to translate. Translations are generated, again, by their unitary transformations, but what are the infinitesimal generators for translation, for spatial translation? The momentum. That's what momentum is. A translation, let's say about the x-axis, where you push everything along the x-axis by an infinitesimal amount. That's again of the form 1 plus I times a parameter. The parameter now would correspond to the distance that you push things, the distance that you translate. Again, let's call it epsilon. It's not an angle now. It's a distance times the x component of momentum. This would be a translation along the x-axis, translation along the y-axis, 1 plus I epsilon py, and so forth. So this would be the group of translations. This would be the group of rotations. What about commutators between rotations and translations? Would you expect them to commute or not? Think so? How about commutation, first of all, among just translations? You translate something this way, then you translate it this way, then you translate it back this way, and then you translate it back this way. Translation along x, y, invert the x, and then back. What do you get?
Same thing.
Well, when you translate something or when you rotate something, you first have to apply a force to move it.
Well, we're not talking about literally moving things. We're talking about just imaginary transformations. No force here.
Well, all I'm saying is that you have to do it, then you have to undo what you did to make it do it. So you've got actually 4 actions involved. In other words, you have to start it and stop it, and then you have to start it and stop it again to undo it.
These are not actual motions of a system. They're just asking, what would the state of a world be like if you displaced everything? They're not saying displace it. They're saying, what would the state be if you did displace it? A little bit of a difference. It's mathematics, not physics. Yeah. Yeah, just a mathematical description of a displaced thing. If you displace along an axis, and then you displace along another axis, and then you displace back along the first axis, and then you displace back along the second axis, you come back to the same place. Okay. That's a property of Euclidean space. So what does that tell you about commutators of momenta? They're 0. Commutators of momenta are 0. Okay. Now, let's try to see what would happen if we take a point, first translate it. We translate by 1 unit in this direction. Now rotate by an angle, let's say by an angle theta. All right, so we rotate from here up to, let's say, over here by this angle theta. That's the angle theta. And then we translate back, translate along the same axis back, and then undo the rotation. Where do we come to? Do we come back to the same point? No. We come back to about over here someplace. So it's clear that translations and rotations don't commute. Translations and rotations don't commute. And if you work it out, it's not hard to work out. You do little translations, little infinitesimal translations, and you can work out what the commutation relations are between the rotation generators and the translation generators. I'll tell you what they are. They're just commutator of Lx. Well, let's just do it in 2 dimensions. Li with Pj is I epsilon ijk pk. That's it. But this is not important. This is not important. What's important is the idea that everything is kept track of by these commutation relations. All right, that's the first thing about groups. Groups are really commutator algebras in disguise, or vice versa. Next thing about groups in quantum mechanics. First of all, they're symmetries, but they tell you something about the energies of different configurations. Naively, it's clear. Naively, it's clear what they say. They say that if you perform one of these symmetry operations and you really have a symmetry, it should not change the energy of a system. If you have an object, whatever that object is, and it has a certain energy, and you just rotate it, it shouldn't change its energy, right? Or if you just translate it, it shouldn't change its energy. So if you have a legitimate symmetry, then the conclusion should be that when you perform a symmetry operation, the energy of a state shouldn't change. Let's see what that says. See mathematically if we can see what that says. What the requirement is. Okay, so let's suppose we have some state, any state, and it happens to have energy E. Let's say it has energy E. It's an eigenvector of the energy, has a definite energy, let's call it E. And now let's apply a small transformation to it. Let's call it U. Let's take U. U is, it doesn't have to be small, just a transformation of the appropriate kind, translation, rotation, isospin transformation, anything that corresponds to a symmetry of the system. And now ask what the energy of the resulting state is. We find the energy of the resulting state. Well, let's first of all say what this means. What this means, that it's a state of given energy, means that it's an eigenvector of the Hamiltonian with eigenvalue E. Right? That's the definition in quantum mechanics of saying a thing has a definite energy, that the Hamiltonian acts on it to just give the eigenvalue back. It's an eigenvector of energy E. Okay, now let's ask about this state. If the original state was an eigenvector of the energy, and we have a symmetry, then the resulting state must also be an eigenvector of the energy, right? So that must say that the Hamiltonian on this state must be equal to the energy times the same state, U E. Okay. But this is also equal to H UE. What did I just do? I just said that the energy times U times E can be replaced by, put the Hamiltonian over here. Why? Because H on E just gives E times E. All right, so now I just subtract. HU minus UH on E equals 0. That's what the conclusion is if a symmetry operation doesn't change the energy, right?
So what was the first relation that you had up there? H or U times?
Okay, let's go through it again. Let me go through it again. This is tricky. We start by saying we have an eigenvector of the energy. H on E equals E on E. This says that E, the eigenvector E, is an eigenvector of the Hamiltonian with energy E. Okay, step number one. All right. Now, I assert that U times E has exactly the same energy. Why? Because U is a symmetry. It rotates, or it does something that's just really a coordinate. It translates, it rotates. It doesn't do anything important to the system. This must have the same energy, and so this must also be an eigenvector of the Hamiltonian. Let's write that. H U E must equal E U E. Okay, let me draw. E is just a number, except if it's in a vector, then it's a vector. All right? H times this vector here must equal E times the same vector. Okay? That's the statement that U times E is also an eigenvector of the energy. Okay. Now, E is just a number, as Michael said, so it can be brought inside here. Doesn't matter which side of U it's on. It's just a number. U times E. Fair enough? I didn't do anything. I just interchanged the numerical number E with the operator U. But now, E times the vector E is H times the vector E. So I can say that this is U, H, E. Equals this one over here. And now I come to the marvelous conclusion by transposing that H times U minus U times H acting on E is equal to 0. For an eigenvector of energy E. But this has to be true not for one particular eigenvector of the energy, but for all eigenvectors of the energy. For any eigenvector of the energy, this must be true. If the energy eigenstates are a complete basis of states, then it follows mathematically that H times U minus U times H must itself be 0. If something is true, if something gives 0 on every vector, or every eigenvector of a particular operator, then that thing must be 0. So the conclusion is, if you have a symmetry, it means that the symmetry operations commute with the Hamiltonian. All right, so that's the signal, or that's the not the conclusion, that's the criteria for whether a set of transformations like U are symmetries or not. They must commute with the Hamiltonian. All right, so here is every symmetry, whatever it is, commutes with the Hamiltonian, and that's equivalent to saying that the symmetry operations do not change the energy of a state. All right, so as an example, take a state of a spin pointing in a certain direction. Rotate it. What happens to the energy of it? The answer is nothing. Why not? Because rotation is a symmetry. Put the spin in a magnetic field. What happens if you rotate the spin in the magnetic field? It will change its energy. But the reason, of course, is because you're not really doing a symmetry operation. You're rotating one thing relative to a thing which you're not rotating. What would happen if you did a true symmetry operation? That would mean rotate the spin and also rotate the magnetic field. That would not change the energy. Okay? Same thing, for example, you have a particle, let's say an electron. Here's an electron in the field of a proton. What happens if you translate the electron? Does the energy of the electron stay the same? Of course not. The electron have to do work to move it against the proton. So you say, oh, translation of the electron is not a symmetry. No, translation of an electron by itself is not a symmetry, but translation of the whole thing is a symmetry. All right, so translation being a symmetry, rotation being a symmetry says that those operations commute with the Hamiltonian. Now, if every U commutes with the Hamiltonian, let's come back to the generators. That says that the generators commute with the Hamiltonian. If every operator of the form 1 plus I epsilon L commutes with the Hamiltonian, 1 commutes with everything. The commutator of 1 with anything is 0. I and epsilon don't matter here. It says that all of the components of the generators of a symmetry commute with the Hamiltonian. What else can you say that commuting with the Hamiltonian means? If you go back to your quantum mechanics, yeah, the time derivative of the thing which commutes with the Hamiltonian is 0. So one says that symmetries imply conservation laws, or conservation laws imply symmetries. It's not important which. All right, so I've simply repeated everything that we've talked about before about symmetries, but mostly to remind you of that. Momentum conservation, angular momentum conservation, all associated with symmetries. And of course, there are plenty of other symmetries around. Now,
So it looks like the external field has to have that symmetry.
either the external field has the symmetry or you have to rotate the external field, right? Right, okay? But important thing is that rotation does not change the energy, or not just rotation, but symmetry operations don't change the energy. That's the reason that the different components, let's say we have electrons in orbit around in a particular orbit around a nucleus. Okay, so the orbits are characterized by a total angular momentum and the z component of angular momentum. The different z components of angular momentum can be rotated into each other. They get mixed up with each other under rotation. The total angular momentum, L, doesn't change under rotation. It's the total magnitude of the angular momentum. But the various z components of the angular momentum do rotate into each other. And the symmetry under rotation tells you that all the different states of an atom at a given L, but for different m. Everybody know what m is for an atom? M is the magnetic quantum number. It really corresponds to the z component of angular momentum. The different components, z components, have the same energy as a consequence of rotational symmetry. All right. All of the symmetries that we've discussed up till now have one characteristic in common. When they act on bosons they give back bosons. When they act on fermions, they give back fermions. What happens to a boson? What happens to an electron if you rotate it? Stays an electron. Doesn't turn into a photon. Quarks have symmetries under the color transformations. Remember the color transformations? Mixes up the three colors of quark. Takes a quark into a quark. It doesn't take a quark into a gluon. A gluon is a boson. A quark is a fermion. In fact, all of the symmetries we've talked about up till now don't change the spin of a particle. It would take scalar particles to scalar particles, half-spin particles to half-spin particles. Generally speaking, the symmetries we've talked about don't do anything to the spin, don't do anything to the type of particle, don't do anything to the charge of a particle, keep the charge of a particle unchanged, and especially don't do anything to the mass of a particle. In some way, the symmetries tell you that there are equalities between masses of different states. For example, they do tell you that the various z components of angular momentum all have the same energy, because you can rotate one into the other. Z components of angular momentum in an atom, as long as the atom is not in an external magnetic field or electric field. All right, supersymmetry is a new kind of symmetry. It's a really crazy kind of symmetry, which, when it acts, it takes a fermion into a boson or a boson into a fermion. Just like the rotations tell you that there have to be these multiplets with different z components of angular momentum, that if there's a z component of angular momentum which is plus a half, then rotation symmetry tells you there has to be one of minus a half with the same energy. If there's a spin up with 1 unit, then it's enough to tell you there'll be a spin down with 1 unit. But if you look carefully at the mathematics, you'll also find out that there has to be one of 0 in between, all of exactly the same energy. That's what a symmetry does for you. As I said, supersymmetry is a very strange new construction which, when it acts, takes a fermion to a boson. The mathematics of it is very weird, very strange, very non-classical, extremely non-classical, and absolutely impossible to visualize in any sense. So I will tell you a little bit about the mathematics of it. Why is it important, incidentally? It's important because if you have a theory that enjoys this symmetry, that has this supersymmetry, then there will always be, for every fermion, a boson with exactly the same mass, and with every boson, a fermion of exactly the same mass. That's exactly the situation that we were looking for, where bosons and fermions might be able to exactly cancel out infinities or large renormalization effects that we discussed for a couple of times already. This is very, very hard to motivate. This is hard to motivate because it is so completely unintuitive, very unintuitive. These are symmetries, as I said, which take fermions into bosons. The generators of them are called Q. There's a Q. There are several generators called Q. We'll just call them Q for the moment. And they take a boson into a fermion. Something totally new. These Qs, let's see, I'm trying to figure out how to say this right. Okay. How can we make an operator which takes a fermion into a boson or a boson into a fermion? Let's think about that for a moment. Q is an operator which can take a fermion into a boson and a boson into a fermion. What kind of operator could do that? Well, it's very easy, actually.
Operate on the spin. Just operate on the spin.
And charge.
Well, it has to, what does it have to do? If you have a boson, it has to remove the boson and put back a fermion. Right? If there's a fermion there, it has to remove the fermion and put back a boson. I'll construct for you a Q that does exactly that. We have creation and annihilation operators for fermions and bosons, right? All right, let's, what do we want? Q, which takes a boson to a fermion. It has to annihilate a boson. So let's put an annihilation operator. Let's see, I always forget. Is A a creation? A dagger is creation, right? So A is annihilation. This annihilates a boson. So just for the simplest thing, this annihilates a boson, any annihilation operator, and then what do we want to follow it by? A creation operator for a fermion. What did we call creation operators for fermions? I can't remember. C dagger, right? C dagger. C dagger. Here's an operator which whenever it acts on a boson will always give a fermion, right? What happens if it acts on a fermion? It gives nothing, right? It just annihilates the fermion. So let's add something to it. Let's add to it A dagger times C. This annihilates a fermion and creates a boson, right? So what does this object do to a boson? Well, this eats the boson and spits out a fermion. So it creates a fermion. What about this piece of it? This piece of it annihilates a fermion, but there is no fermion. So this piece of it is dead. This relationship is correct. What happens if the same operator acts on a boson? A dagger, oh, this is a boson, on a fermion, plus C dagger A. What does that do on a fermion? Well, this one annihilates a boson, but there is no boson there. So, nothing. This one annihilates the fermion and puts back a boson. So this one puts in a boson. So, yes, we can make operators which do have the property that they intertwine between fermions and bosons. Okay?
Superpositions?
Superposition.
Does this imply you can get a superposition particle of a fermion and a boson?
Well, if it acts on a superposition, it will produce a superposition. But if it acts on a boson, it makes a fermion. If it acts on a fermion, it makes a boson. And it won't make a superposition by itself.
It's not a state that's an operator. I think what he was thinking was this is some kind of a superposition state, but really it's just an operator. You created
this is an operator. Yeah, this is an operator. If it acts on a general state, it will make a superposition. But if it acts on a boson, it makes a fermion. If it acts on a fermion, it makes a boson. What happens if it acts on the vacuum? What does it do if it acts on a vacuum?
What's the vacuum?
Gives you the vacuum, doesn't it?
Doesn't it? No. It's made a pair.
No, it doesn't make the vacuum. It just makes zero. Why does it make zero? Let's try it on a vacuum.
Oh, yeah. Right.
A annihilates a boson, but there is no boson. C annihilates a fermion, but there is no fermion. You just get zero. Not the vacuum, but just zero, the zero vector. Okay? So the one exception to the rule, what the rule being that when it acts on a fermion, it creates a boson. When it acts on a boson, it creates a fermion. The one exception to this rule, I don't know if it's an exception to the rule, just a funny exception, is that when it acts on the vacuum, it just gives zero. So this is a class of operators which has the properties of a supersymmetry generator. Supersymmetry generators are of this form. They involve fermions and bosons in a way that is mixed together like this. Now, the question is, here we can
The question though about the dimension of that vector,
dimension of what?
the state vector, and for bosons, the boson state vector is usually
State
different dimensionality from a fermion state vector, isn't it?
Okay, now what do you mean by dimensionality?
Well, let's say a half-spin particle would have two dimensions.
Two components, yes, yes. So for example, yes. So for example, yeah, good. You're now telling me a little more about this operator Q. So let's suppose it acts on a boson and the boson is spin 0. It creates a fermion, but a fermion has a spin 1/2, and a spin 1/2 particle has two components. So does it create the spin up or does it create the spin down? Well, the answer must be, if we're going to make any sense out of this, that there can't be just a single Q, there has to be two of them. One which takes the boson into the up fermion and one which takes the boson into the down fermion. There has to be another index. Qs always have indices, and the index is always a half-spin index. It itself is a half-spin index because it has to be able to change the spin by half a unit. Now, what happens if a Q with a spin I acts on a fermion? A fermion also has to have an index. It's either up or down. So we ought to put indices on these fermion vectors here. What happens if it acts on a Fj? Well, basically the answer is if I is the same as J, it makes the boson. If I is not the same as J, it makes nothing. Okay. So whatever these operators are here, whatever these symmetry operators, the generators, these are the generators of supersymmetry. The generators of supersymmetry not only they're fermionic. They're fermionic in the sense that they have an odd number of fermion operators in them. They have an odd number of fermion operators. Every interesting quantity that we've been experiencing up till now, things that we measure and so forth, always have even number of fermion operators in them. Supergenerators have odd number of fermion operators because they've got to change the fermion number, and they also have indices. The indices are spin indices. All right, really understanding supersymmetry and fermions and fermionic symmetries. Why do I call them fermionic symmetries? Because the generators themselves have odd numbers of fermions in them. They change a fermion into a boson. Really understanding that the mathematics of it really does entail a generalization of arithmetic, of the notion of numbers. Let's just remind ourselves of one thing about fermion fields and boson fields, or just fermion operators, creation and annihilation operators. Good enough. Fields are made up out of creation and annihilation operators. Let's just remind ourselves what we know about creation and annihilation operators for bosons. Creation and annihilation operators for bosons have commutation relations. The commutation relations are commutator of A with A, and this could be any creation operator, any bosonic creation these are annihilation operators, aren't they? What's the commutation relation of an A with an A? 0. In fact, they could be different. They could be for different bosons. Even so, they commute with each other. What about a dagger with a dagger? Same. What about A with a dagger, or is it a dagger with A? I think it's that way. What does that give? 1. That's the algebraic properties of bosonic operators. In particular, this could, this particular relation over here, or let's take this one over here, this could actually stand for two different creation operators. One, let's say, for a particle of one momentum, one for a particle of another momentum, or for a particle at one place and a particle in another place. Let's take this relationship here and create a two-particle state, two bosons, one with label I and one with label J. As I said, label I and label J could represent momentum, they could represent position, they could represent anything you like. How are we going to create two of them? We're going to create by just applying the creation operators. This is the state of two bosons, one of type I and one of type J. How does this differ from a state with the same exact particles, but in which they've been introduced in the opposite order? It doesn't differ. It's exactly the same thing. It's exactly the same thing, and mathematically, the commutation relations here tell you that A dagger I, A dagger J is the same as A dagger J, AI. They're equal to each other. This is the symmetry of wave functions under interchange of bosons. When you interchange the arguments of the wave function, or the labels labeling the states, here these are related to each other just by interchanging I and J, it does nothing. It multiplies the state by the number 1. That's the character of bosons, and the character of bosons is indicated by commutation relations between fields, or between the things that make up the fields. What about C's? Okay. What about the commutator of two C's? Let's go after this one here first. C dagger. Is that one? No. That's not the way we do things with fermions. With fermions, it's anti-commutator. What does anti-commutator mean? It means C dagger plus C dagger C. C dagger plus C dagger C, not minus. Let's see what that means. In fact, every place where you saw commutator, replace it by anti-commutator. What does anti-commutator mean? Anti-commutator of two things, A with B, means AB plus BA. Okay? AB plus BA. Okay, first of all, let's see what this says. What does this say about two particle states? First of all, suppose there's only one kind of fermion, just a C with no label. Anti-commutator of C dagger with C dagger just means C dagger plus C dagger, C dagger. It just means twice C dagger, C dagger. That's equal to 0. So it just says when you multiply C dagger by itself, you get 0. That doesn't mean that C dagger is itself 0. C dagger creates a fermion. What does it mean to say that when you square it, you get 0? It simply means you can't put two fermions into the same state. You simply can't put two fermions into the same state. That's the Pauli exclusion principle. So the Pauli exclusion principle is simply obtained from the anti-commutation relations. Now, supposing you happen to have two different kinds of fermions, they might be the same kind of fermion, an electron, but they might be an electron at one place or an electron at another place, or an electron of one momentum, an electron of another momentum, or they might just be different spin states of the electron. Let's suppose, again, there are two labels. Now, let's make them fermions now. C dagger I, C dagger J. How does that relate to the state C dagger J, C dagger I, where I've interchanged the I and the J? Well, the anti-commutation relations say that C dagger I, C dagger J, plus C dagger J, C dagger I equals 0. Another way of saying it is that C dagger I, C dagger J is minus C dagger J, C dagger I. This is the anti-symmetry of the wave function of, or the anti-symmetry of fermion states with respect to interchange of the labels of the fermions. Okay. So the character of fermions and the character of bosons is encoded in these commutation or anti-commutation relations. Whatever fermions are, or whatever the mathematics of fermions are, it's related to the mathematics of bosons by replacing commutator by anti-commutator. But particularly, the property of the square of a fermion operator being 0 is very, very different than the square of a boson operator. Now, boson fields, when you build up a large number of bosons, behave very classically. When we have a large number of photons, we think of the fields as the electric and magnetic fields, and we think of them as ordinary numbers. We think of them as ordinary numbers, and ordinary numbers commute. Ordinary numbers commute. What about fermions? Well, in fermions, you never build up large numbers of fermions in the same state. So field operators for fermions never get big. They never get big because their square is 0, so how can they ever get big? There's a whole generalization of arithmetic, which I'll tell you a little bit about, just a little bit, in which the numbers of arithmetic are replaced by numbers which anti-commute instead of commute. And these numbers are extremely useful. They're really just bookkeeping devices. They're bookkeeping devices the same way that fermion fields are bookkeeping devices. They keep track of various relationships. These are not real numbers. These are not numbers that you can measure. They're not numbers that experiments can be answers, that can be answers to experiments. They're bookkeeping devices. They're called Grassmann numbers. A whole theory of new kind of numbers. As I said, it's a generalization of arithmetic, and I'm just going to tell you a little bit about it, because fermion fields are really Grassmann numbers. They're really Grassmann numbers, and the generators of these fermionic symmetries, these things which take fermions to bosons, are also Grassmann numbers. Grassmann numbers have the property that they anti-commute. So let me just tell you a little bit about them. For our purposes now, they're really just a curiosity, but they really are at the heart of what supersymmetry is. So we have a collection of ordinary numbers to begin with. Let's call them ordinary numbers. Let's call them alpha sub I. I just labels which number we're talking about. Okay? And I'm just labeling them alpha sub I. Here's something which is true of any pair of ordinary numbers. Alpha sub I, alpha sub j is equal to alpha sub j, alpha sub I. That's 3 times 5 is 5 times 3. Okay? Now we're going to invent these new numbers called Grassmann numbers. We're going to call them theta instead of alpha. Theta I. I don't know how many there are. There might be only one of them. There might be 2 of them. There might be 3 of them. However many there are, they have the properties that theta I anti-commutes with theta j. In other words, theta I, theta j is equal to minus theta j, theta I. When you interchange them, they change sign. That's one of the characters of Grassmann numbers. Now don't ask me what the value of theta I is. It's not 7, it's not 6, it's just theta I. It doesn't have any ordinary numerical value. Another thing you can say about them is their squares are 0. Theta squared, which is equal to, let's say theta 1 squared. Theta 1 squared is just theta 1, theta 1. But theta 1 is just 1/2 of theta 1 plus theta 1, theta 1. And theta 1 plus theta 1, that's just the anti-commutator of theta 1 with theta 1. So theta squareds are equal to 0. Now, let's suppose, for simplicity now, let's suppose there's only one Grassmann number. Let's just call it theta. One Grassmann number. It's like just having one number in arithmetic, the number 7. Okay. Oh, we'll also add an ordinary number. We can have both ordinary numbers and Grassmann numbers in the same arithmetic. I should tell you about, okay, so we should have, if we take an ordinary number, a commuting number, let's call it an alpha, the rule is ordinary numbers commute with thetas. They don't anti-commute with thetas, they commute. All right, they commute with themselves. The only thing that anti-commutes is a Grassmann number with itself. Grassmann. No, Grassmann. No, grass, the kind you smoke. Grass. Grass. Grassmann. Grassmann must have been a mathematician, a German mathematician from the 19th century. Now, he was clearly smoking something when he invented this. I mean, you know. What? Ah, good. A Grassmann number times an ordinary number is a Grassmann number. Right. Right. That's right. We can easily prove that Grassmann numbers times ordinary numbers are ordinary numbers. What about a Grassmann number times a Grassmann number? Though a Grassmann number times a Grassmann number is ordinary. What about an ordinary times a Grassmann? It's a Grassmann. Right. Now, so ordinary times ordinary is ordinary. Ordinary times Grassmann is Grassmann. And Grassmann times Grassmann is ordinary. Okay, so it's like odd and even numbers. You know, odd times odd is even times even is even, odd times times even is odd. Okay, so that's the property of Grassmann numbers. Okay, what's that? Okay, so let's think. A real times a real is a real times imaginary is imaginary, and imaginary times imaginary is real. So yes, it's also true of imaginary and real numbers. But it's particularly true of these. Now, what is unusual is that the square of any Grassmann number is 0, because it anti-commutes with itself.
Is that the same as the cross product, like in free space?
What's that?
Is it like the cross product?
No. No.
I mean, the cross product of the same things is 0, right?
Okay, yeah, I mean, the cross product of A times B is minus the cross product of B times A. That's true. That's true. But, yeah, I don't think the analogy goes too far, but yes, that's right. Okay.
Can't you think of this as a generalization of like imaginary numbers? Like
It's just a generalization of numbers. It's a generalization of numbers where you replace commuting. One of the postulates of arithmetic is that multiplication commutes. Here, the postulate of arithmetic is that multiplication anti-commutes. Okay. Let's take the case of only one Grassmann number. Okay? Then the number, and think about functions. Let's think about functions now of Grassmann numbers. We'll have Grassmann numbers and ordinary numbers. Ordinary numbers are ordinary, but there's only one Grassmann number. Okay, only one Grassmann number. The functions of Grassmann numbers are very limited. Let's see what kind of functions we can build of Grassmann numbers. Well, we can start trying to build polynomials. A polynomial might be an ordinary number, any ordinary number, let's call it alpha, plus another you can multiply Grassmann numbers by ordinary numbers. So the next thing you can build is beta times a Grassmann number. There's only one Grassmann number now. Now let's try to build a quadratic polynomial. Let's call it plus alpha beta gamma times theta squared. But theta squared is 0, so we've run out. There are linear polynomials, and that's it. Those are the most general functions of a single Grassmann number. The space of functions is not very rich. Okay? It consists of basically two functions, a constant and a linear function of the Grassmann number. No more. There are no more functions than that. So it's a pretty damn simple arithmetic, or a pretty damn, yeah.
The theta cube would also be 0.
Or theta cubed is theta times theta squared, and if theta squared is 0, theta cubed is 0. So everything beyond theta, theta is 0. That's it. There's not much of a space of functions. Okay. Let's suppose that there are two Grassmann variables, theta 1 and theta 2. Then what kind of functions are there? Well, again, there's alpha plus beta theta 1, beta 1 theta 1, let's call it. We can then add plus beta 2 theta 2. Beta 1 and beta 2 are just ordinary numbers. Ordinary numbers could be complex numbers. It's not important at the moment whether they're complex numbers or real numbers, whatever they happen to be. And then we can have plus gamma theta 1 theta 2. Theta 1 times theta 2 is not 0. Theta 1 squared is 0 because it anti-commutes with itself. Theta. It's a commuting number, but it's surely not an ordinary number. Why isn't it an ordinary number? Because it is not 0, but its square is 0.
Yeah.
Theta 1, theta 2, theta 1, theta 2, that's 0. So it's surely not an ordinary number. Okay, it's not 0, but its square is 0. But it does have the property that it commutes with things. All right, so that's it. That's the last. That's the biggest function. That's the most complicated function you can make of two thetas. Incidentally, this is not equal to alpha plus beta 1 theta 1 plus beta 2 theta 2 plus gamma theta 2 theta 1. Why not? Because they anti-commute, and that means to make them equal, you would have to put a minus sign here.
Question.
Yeah.
You said you multiply an ordinary number times a theta, you get a theta. So it seems like beta times theta would give yet a third. Or fourth. Beta, you multiply beta times a theta 1, that seems like that would give you a different theta. But you're saying there's only two thetas in that equation.
No, you can, you can multiply a theta by a real number. Yeah, you can multiply it by a real number. Right. So what should we say? We should say that thetas, there's only two of them up to, they really form a two-dimensional vector space. Right. So apart from multiplication by an ordinary number, there are really only two of them. Okay, so the space of functions is very limited. There's not much structure to it. If there are three thetas, well, it gets a little bit longer. You can go up to beta 3 theta 3, then you can have theta 1 theta 2, theta 1 theta 3, theta 2 theta 3, and then finally theta 1 theta 2 theta 3, and that's it. Okay? So Polynomials in this theory are polynomial functions of theta. Polynomial functions of theta are very limited. And there are no non-polynomial functions. Okay. What about exponentials of theta? That's an interesting question. Let's see what exponentials do. Let's see if e to the a, let's say there's only one theta. I think we can do this with just one theta. E to the a theta times e to the b theta. Oh, let's do this first. E to the a theta times e to the b theta. Is that equal to e to the a plus b, a to the a theta, you know, the things add in the exponent. All right, so let's see. E to the a theta is 1 plus a theta plus a squared theta squared over 2 factorial plus a cubed theta cubed over 3 factorial, but we're dead after theta. So e to the a theta is just 1 plus a theta. E to the b theta is 1 plus b theta. The product of these is 1 plus a theta plus b theta plus ab theta squared, but theta squared is 0. So this is 1 plus a plus b theta, and that is just e to the a plus b theta. So exponentials exist, or the algebra of exponentials is exactly the same as the algebra of exponentials of ordinary things, but exponentials are no more complicated than this. I'm curious. Let's see if it works with 2 thetas. 2 different thetas. Let's try it. Okay, so we have e to the theta 1, e to the theta 2. Okay, let's see what we get. We get 1 plus theta 1 times 1 plus theta 2, which is equal to 1 plus theta 1 plus theta 2 plus theta 1 theta 2. I think that's right, isn't it? And that's it. That's as far as we go. Okay, let's see if that's equal to e, I hope it is, e to the theta 1 plus theta 2. This should be equal to 1 plus theta 1 plus theta 2 plus theta 1 plus theta 2 squared over 2 factorial, right? Over 2 factorial plus higher. But the problem with higher is we're not going to get anything. The reason we get something from here is because we have theta 1 times theta 2. Theta 1 squared is 0, theta 2 squared is 0, but we do have twice theta 1 theta 2 over 2 factorial, which is exactly what appears here. But now what happens when you go to theta 1 plus theta 2 cubed? That's going to have things like theta 1 cubed, that's 0. It's going to have things like theta 2 cubed, that's 0. It's going to have theta 1 squared times theta 2, that's 0 because theta 1 squared is 0. In other words, there's always going to be some repetition of one of the thetas. And a repetition means that it's equal to 0. So this thing is not there. And yes, it does reproduce this. Interesting, just an interesting fact. Exponential functions exist, but they're extremely simple.
Doesn't the square term there give you theta 1, theta 2 plus theta 2, theta 1, which is 0?
No, no, it doesn't. It doesn't. Let's see why that. That's a good point. Why doesn't it? Theta 1 plus theta 2, theta 1. You know, you may be right. That looks right. Theta 1. Theta 1 squared plus theta 2 squared plus theta 1 theta 2 plus theta 2 plus theta 1 Yeah, no, that's worrisome.
Does this, does theta 1 plus theta 2 give you another theta type of thing? Another object?
Is the sum of two Grassmann numbers another Grassmann number?
Yeah, sum of two Grassmann numbers is another Grassmann number. So the question, yeah. Looks like the exponentials don't always make sense. I didn't know that. It looks like there is a failure of multiplication of, am I missing something? I don't know. Looks like it doesn't work. I actually didn't know that. That's the first time I ever tried that. What's that? Yeah, that third term is 0. No, but this is not 0. Theta 1, theta 2 is not 0.
Is it possible that if you go to cubed, you might get that term?
What's that?
If you go to the cubic thing, you might get that term?
If you go to the cubic thing, I don't think so. Theta 1? No, I don't think so. I don't think so. No, I think it fails. I think it really does fail. I'll check it.
Just a dumb question. You have 1 plus theta 1. What does that mean? Because you have an ordinary number as a Grassmann number. Is that an ordinary number?
No, 1 plus theta 1 is not an ordinary number. Yeah, you're allowed to mix them. You're allowed to add them. You're allowed to add them. You're allowed to add them, but it looks like you can't exponentiate them and get the I'm confused by it. I thought you could, but
A little bit like rotations about different axes, aren't they?
they are what they are. I don't think they're like anything else. I don't think they're like anything else. They're a bookkeeping device which is useful, but they're not like anything else. They're Grassmann numbers. Functions of Grassmann numbers can be differentiated and integrated, which is a useful bookkeeping device. When I say they can be integrated, I mean you can define the integrals of a Grassmann number and the derivatives so that it satisfies certain properties. If you have the derivation, the derivative of a function of a Grassmann number is straightforward. The derivative with respect to theta of 1 or any 1 or any alpha is equal to 0. The derivative of theta with respect to theta is 1. And so, for example, if we have just one theta in a problem, we have functions a plus b theta. The derivative of that with respect to theta is very straightforward. It's just beta. That's it. Supposing we have more than one theta. This is easy. I mean, this is just ordinary derivative. And this is definition. This is definition. The derivative with respect to theta 1 of a function alpha, but there are two thetas now, just as an example. Two thetas, alpha plus beta theta 1 plus beta 2 theta 2 plus finally gamma theta 1 theta 2. All right, you go through it just as if it was an ordinary function. Derivative with respect to theta 1, you find something from here, just beta 1. Nothing from here, nothing from here, and from here you have gamma theta 2. So this is exactly what you would expect. The only surprise in the definition is that if I were to differentiate with respect to theta 2, nothing from the alpha, nothing from here, beta 2. But what about here? You might expect theta 1, right? Okay, the rule is that the derivative operation is also like a Grassmann number, and when you pass it through another Grassmann number, it changes sign. The rule for Grassmann numbers is when you pass them through each other, they change sign. The derivative of a Grassmann number is counted as a Grassmann number with respect to sign. So that means when you pass it through theta 1, you change sign, and this will give you minus gamma theta 1. So you treat derivatives the same way you treat the Grassmann numbers themselves. A derivative with respect to a theta is also a Grassmann kind of variable, and when it passes through any other Grassmann variable, it changes sign. That's the only peculiar thing about differentiation with respect to Grassmann numbers. Incidentally, these rules ensure some of the rules of ordinary differentiation. For example, they ensure the rule that the derivative of a product is the first term times the derivative of the second one plus the second one times the derivative of the first one, the usual rule of calculus for products. If you didn't change the sign here, you'd get into trouble with that. So the calculus of Grassmann variables is, again, simple. You don't do anything unusual except to remember that whenever a derivative passes through a Grassmann variable, the thing changes sign. Okay. We have to do integration of Grassmann variables, which is too late for now. We will be able to write a table, since there are so few Grassmann functions, the table of Grassmann integrals will be about that long. Okay? So we'll also define Grassmann integrals. Why I'm doing this is just to show you that there does exist a sort of mathematical algebraic framework in which supersymmetry and in which fermion operators fit into a new kind of arithmetic. It is essential to understand all of this, to understand supersymmetry at its deepest level.
It looks like the product of any two Grassmann numbers is 0, with the same number.
No, a theta 1 times a theta 2 is not 0.
Add theta 1 and theta 2 and square them. And if that's 0, you'll see the product is 0.
No, it's not true that the square of...
Okay, square that. And we know that's 0.
You square anything at 0, right?
Yes, it is.
Yeah, and therefore the product of any two Grassmann numbers is 0.
No. No, you see, this is equal to theta 1 squared plus theta 2 squared plus theta 1 theta 2 plus theta 2 theta 1. Right. Not quite true. Right. This plus this.
Well, yeah, the result is 0, but it doesn't prove that.
Yeah, it doesn't prove that theta 1 theta 2 is equal to 0. It just proves that theta 1 theta 2 plus theta 2 theta 1 is equal to 0. Yeah, that's already a rule. Right. So theta 1 times theta 2 is equal to minus theta 2 theta 1, but theta 1 times theta 2 is not equal to 0. Good. But I'm still puzzled about this exponential. I had always thought that, I never used it for anything, and I don't know what it's good for, but I was hoping that exponentials existed.
Well, anytime you have the sum of the two things, powers of the sum of two things, once you get to the square, it's all 0.
Yeah, but if you multiply e to the theta 1 times e to the theta 2, it does look like you get left with a...
It looks like you have a source of theta 1, theta 2.
You do have a theta 1 theta 2.
I'm saying that this expansion of the exponential gives you square terms and higher, but square terms are automatically 0.
Yeah, so that means this is true.
That can't go any further. And
Right.
no source of theta
But that's not the same as this. So it's simply not the case that this is equal to this. Simply not the case.
But aren't you assuming that the expansion is valid? Aren't you assuming that the exponential expansion is valid? That may not be the case.
Oh,
right?
yeah. That was the definition of the exponential. Yeah, I think there may be some other there may be some other definition. I have to think about it. There may be another definition.
For more, please visit us at stanford.edu.